Here's our diving board, and it's being held up by these two posts over here. And it says that the posts are some distance d apart. It names that distance in the problem. And the diving board is some length L, from one end to the other. That's given in the problem as well. And there's some guy standing here on the end. And we're asked to find the forces in each of these posts. Well, the first thing we maybe better figure out is which way both the forces go. The posts could push up or down. Now, if both the posts pushed up, that would cause a clockwise rotation. And the guy pushing down on this end is also causing a clockwise rotation, so that would make the whole board tip clockwise. And so can't be what's happening. One of them has to be pushing down. Now, if this guy is the one that's pushing down and this one's pushing up, then we have two downward forces on this side and an upward force on that side, and that would all be clockwise again, and that wouldn't work. So what it has to be is that the left one is pushing down and the right one is pushing up. So now that we figured that out, let's draw our torque diagram. There's a picture of the board. I'm going to draw in the forces. We have mg for the guy over here. We might have had an mg for the board right in the middle of the board, but it said that the mass of the board was negligible, so we don't have to do that. And then we have these two forces over here, the one from the left pedestal and the one from the right pedestal. I'm going to call them L for left and R for right, because that's easy. So when I do my force balancing equation, which I always like to do, I have one force going up, that's the right force, and two forces going down, the left force and mg. And I know that has to be equal to 0 because it's not moving. Now, this is a great equation and it looks really easy, but I can't use it to solve for either the right force or the left force because they're both in there and there's only one equation. But I might be able to use it later. So, since forces didn't work, I need to go to torques. Now, I noticed from the force equation that my problem was that I had the right and left torques, right and left forces in the same equation. That's why I couldn't solve for it. So what I want to do with my torque equation is to make sure that I get rid of one of them. So I'm going to put my center of rotation on top of one of these forces to give it no lever arm, and then it won't have a torque. So I'm going to put it here on the left one. I could have easily also done it on the right one, but this is just what I'm choosing. So I have my center of rotation here. The left force has no torque, and so I'm just going to deal with these two. I'm going to draw in the lever arms. So this lever arm for this force is that big, and I see from this picture over here that that's D. That's a number that we know. And then the lever arm from the center of rotation to the point of application of force, for this force, that's the whole length of the board. That's L. So now I've got my lever arms. I'm going to go put my angles in. The angle between this lever arm and that force is 90. This angle is also 90, so I have an easy problem. And I'm going to write my torque equation. Remember, I'm going to take the total torque and make it equal to 0. So the first one is dr times the sine of 90. This one is lmg times the sine of 90. I have to make one of them negative because they are rotating in opposite directions. So I'll just go ahead and make this one negative. Doesn't matter which one. And that's going to be equal to 0. So from this I can figure out that the right force is going to be lmg over d. And those are all things I know. I can calculate that. Once we've calculated the right force, we can go back into this equation and find the left force. The left force is going to be equal to r minus mg. And if we've already found r, this part's going to be easy.